This is chapter 11 on radicals and rational exponents. This is brand new stuff. You might be a little familiar, but most of this will be brand new. The first thing you want to do is print what's called the power chart from MyMathLab. You want to print this out. It comes to a page. That way if you lose one or you need a second one, you can make another one. But it's just a half-page handout. You can hole punch it if you like, so it can stay in your binder or tuck it in a pocket somewhere of your binder, so that it's easy to refer to. We're going to be using this throughout chapter 11, and you can use this on the exam as well. It's kind of like a multiplication chart, but it's with powers or exponents instead of multiplying. So these over here are called your bases, and then across the top are your powers or exponents. So in this first box, you're going to be doing 1 to the power of 0. And then in the next box, you're going to be doing 1 to the power of 1. This would be 1 to the power of 2, 1 to the power of 3, 4, 5, all the way up to 10. Same thing with 2. This will be 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the fourth. And you want to fill all these in. You can use your calculator if you like. You want to fill all these in, all the way down to 10. I've grayed out several boxes because the numbers just get way too big. But you want to have a nice filled-in power chart to refer to throughout this chapter. So it should look something like this when you're done. All the different powers, 0 through 10, of the bases 1 through 10, base raised to the power. So I'm going to be referring to this throughout the video, so you want to have this handy. And like I said, hole punch it or tuck it in a pocket somewhere so that you can pull it out whenever you need it to refer to. Alright, so section 11.1 is on what are called radicals. You might have heard that word before, you might not have. Radical is another way of saying square root. So hopefully you've heard of square roots before. But radical is the name of that symbol that we use for square root. And there are several types of radicals. So the one we're familiar with is the square root symbol. Notice there's no number or index in the little arm of the symbol. So we've got square root, where we don't see a number. It would be a 2, but we don't put it. It kind of defaults to be a square root. If you see a little 3 in the, I believe it's called the index in the little arm of the square root symbol, it's called a cube root. Then you've got 4th root, 5th root, etc. 6th root, and it can continue all the way on forever, really. We pretty much focus mainly on square roots and cube roots. We're going to talk a little bit about 4th roots and 5th roots, and you'll start to see some patterns, but the majority of the chapter is focused on square roots and cube roots. So you want to be very familiar, which hopefully you already are, with your perfect squares, and then you'll become more and more familiar with your perfect cubes, like we did with our factoring sum and difference of cubes. It's that same list of perfect cubes. So now I want you to have some 4th powers and 5th powers to refer to as needed. Alright, so let's start by talking about square roots. Hopefully you already know these, and the way to look these up is to find 36 in your perfect squares. So these would be all your squares. These would be your cubes. We know that 36 comes from the base 6 raised to the power 2. So the square root of 36 we normally say is 6. Technically, however, and we'll start seeing this more and more, it could be positive or it could be negative 6, and we'll see this more in chapter 12. But remember, 36 could come from 6 times 6. It can also come from negative 6 times negative 6, because the two negatives would cancel out and still make a positive 36. So anytime we take a square root, technically speaking, you could have a positive or negative result. Same thing here, the square root of 25 could be positive or negative 5. The square root of 9 could be positive or negative 3. So sometimes we'll write plus or minus. For this chapter, we will assume a positive square root unless you have a negative in front of the radical. So if there's a negative in the front of the radical, then we'll make it negative. Otherwise, we'll just assume a positive square root. So let's look at what happens when we throw in some negatives. We have the square root of 36, which we can just assume is positive 6. We have the negative square root of 36, which we can make negative 6. And for this last one, go ahead and get your calculator out. I want to show you how to put that in the calculator. So in your calculator, the square root button is the same button as the x squared key, which is right above log or diagonal from 7. The x squared key, above that you'll see the square root symbol. It's in blue, so we're going to hit the blue second button or the yellow second button, whatever color yours is, and then the x squared key, and it will pull up square root. We can type in 36, it will give us 6. We need the square root of negative, remember the negative's below the 3, negative 36. And it will give you an error. It says non-real answer. So this has what we call a non-real answer. We would think that it would be negative 6, but we know that when you multiply negative 6 times negative 6, you get positive 36. There are no two numbers that are exactly the same that multiply to negative 36. It does not exist. We'll learn more about non-real answers in chapter 12. But for now, when you're trying to square root a negative value, you get a non-real answer. So again, the negative has to be in front of the radical. Very important, outside the radical versus inside the radical. That makes all the difference. Alright, let's look at some non-perfect squares. We can approximate these. The squiggly equals means approximately. We can approximate these by knowing our perfect squares. We can also use our calculator to get a pretty close to exact answer. You'll just round as requested. The homework will tell you how to round. For these, let's round to the nearest hundredth. So the square root of 28 is 5.2915, etc., etc. If we were rounding to the nearest hundredth, the 1 would round the 9 to keep 9. So that's about 5.29. Which should make sense because the square root of 25 is 5, so this will be a little bit more than 5. The square root of 37 should be a little bit more than 6, 6.08, because it's a little bit bigger than 36. So 6.08 if we're rounding to 2 decimal places. The square root of 70 should be 8 point something because we know the square root of 64 is 8. So that would be 8 point, with all those 6's, the second 6 will round the first 6 to a 7. So it should be 8.37. Be careful with your rounding. The homework is very particular about that. And finally, the square root of 42. About halfway between 36 and 49, so we get about halfway between 6 and 7, about 6.48. So if it's a non-perfect square, we can use the calculator. We can't get an exact answer, but we can get pretty close. That's what those squiggly equals means, is approximately equal to. Alright, so let's look at the same idea with variables. This is probably a new concept that you haven't seen before. We have to remember our exponent rules when working with variables. What we're trying to do is think of two terms that multiply to x to the 6th, and it has to be the same term twice. So x to some power times x to some power has to become x to the 6th. Remember with powers, if we're multiplying the bases, we add the powers. So we need two numbers that are the same that add to 6, and that would be 3 and 3. So x to the 3rd is the square root of x to the 6th. And let me take those boxes off so you can really see them. So x to the 3rd times x to the 3rd makes x to the 6th. So the square root of x to the 6th is x to the 3rd. Same thing with x to the 10th. If we split 10, it will be x to the 5th times x to the 5th. And so the square root of x to the 10th is x to the 5th. Another way to think about that, if I were to take that answer and square it, 3 times 2 gives me 6. Or if I were to take this answer and square it, 5 times 2 gives me 10. It's that same idea. Squaring and square rooting onto each other. Alright, so same idea with 14. That would be x to the 7th and x to the 7th. So the square root of x to the 14th is x to the 7th. And then finally x to the 20th would be x to the 10th. The square root is x to the 10th times x to the 10th is x to the 20th. And we'll work with this more. You'll get more comfortable with it as we go along. But you have to remember your exponent properties. And that's true throughout this chapter, your exponent properties. If you want to review your exponent properties from this textbook, it's section 5.1 and 5.5 in this particular textbook. You can also just Google exponent properties or watch a YouTube video on exponent properties just to kind of refresh your memory. But this textbook talks about it in 5.1 and also in 5.5. You'll see some of them pop up as we go along in this chapter. Alright, so let's combine our perfect squares with our variables that we just learned about and talk about what they look like when they're combined. You kind of treat them separately. They are combined, but we really just treat it as two different pieces. The square root of 36 is 6, and the square root of x to the 8th is x to the 4th. So you really just treat them as two separate pieces and just bring them or keep them together. So here we have a negative out front, so my answer is going to be negative. The square root of 49 is 7, and the square root of x to the 18th is x to the 9th. So we're rooting the coefficients and we're dividing the powers. So if you want to write that down, you root coefficients, big numbers, and we divide powers. So your brain has to keep those as two separate operations. You take roots of big numbers of the coefficients and you divide the powers, and it's two separate things. So let's look at this again. The square root of 81 is 9. The square root of to the 50th is x to the 25th. So we're taking the root and then we're dividing. So two separate operations. And again, we'll look at some more combined problems as we go along. Finally, square roots with fractions. Looks intimidating, but the nice part is you can just separate these into two pieces and think about it as two separate parts. So the square root of 4 is 2, and the square root of 25 is 5. So you can just keep them as separate entities and get your answer. It's really not as bad as it looks. So this would be the square root of 1 over the square root of 9. So it would be 1 over 3. If they put it in decimal format, you just have to convert it to a fraction. Hopefully you know that 0.25 is 1/4, but if you don't know, in your calculator, you can type in 0.25, then math, and frac for fraction, and it will convert it into a fraction for you. So if it's a decimal you're not familiar with, just convert it into a fraction. So this is really asking you for the square root of 1/4. We can break that apart. 4 looks like a 9. Let me try that again. And we get 1 over 2. You can also just type this in and it will give you 0.5. So either way is fine. So that's just basics of square roots. We're going to learn a lot more about them throughout chapter 11, but that's just kind of your basics. And let's move on to cube roots. So we might not be as familiar with cube roots, which is where your power chart comes into play. Cube roots come from the third power, so we're going to look at the column for the third power, and then these are all your bases, or your roots. So the cubed root of 8, if I find 8 in my list of cubes, 2 is the base, and that's because 2 times 2 times 2 is 8, so the cubed root of 8 is 2. Same thing with 64. I'm going to look at my list of cubes, find 64, go back and look at the base, which is 4. And that's because 4 times 4 times 4 is 64. So the cubed root of 64 is 4. 64 is also a perfect square, so you have to know if you're dealing with square roots or cube roots in order to know which base you're trying to find. And one more just to practice, 343 comes from the base 7. And that means that 7 times 7 times 7 is 343. So the cubed root is 7. So just stick to your basic cubes. I don't think the numbers get much bigger than 1,000. If they do, there is a way to do this in the calculator. It's a little bit more tricky though. You have to go to math, and I think it's the 4th option down. You'll see the cubed root symbol, and then you can type in your number. Hopefully you won't need that though. The power chart's actually faster and more efficient than the calculator, and you have to remember where that cube root is, which most students will forget. So I encourage you to get comfortable using your power chart, kind of like a multiplication table instead of calculator. So let's look at negative cube roots. This is a little different than square roots. So the negative cube root of 8 works the same. It would just be negative 2. The cubed root of negative 8 is different. So we said with square roots we can't take a square root of a negative, but let's think about the cubed root of a negative. If I have negative 2 times negative 2 times negative 2, these two negatives cancel out, but then a third negative brings it back. So this does have an answer of negative 2, and you can type that in. Type in math, option 4, and then negative 8, negative 8, and it should give you negative 2. So it does work for cubes. Same thing with 125. It would be negative 5, and negative 5. Again, that third piece being negative allows for this to happen, the fact that it's a cube root. And if the negative's on the outside, you still get negative 5. So with cube roots, it doesn't matter where the negative is, you can still get an answer. Alright, let's talk about with variables. I'm going to move this out of the way here. Let's think about with variables. Cube roots split things into 3 pieces instead of 2. So square root splits them into 2. Cube root splits them into 3. So we're trying to find 3 things that are the same that multiply to x to the 6th. And that would be x squared, and x squared. Because we add the exponents, 2 plus 2 plus 2 gives us 6. So the cubed root of x to the 6th is x squared. Same thing here. We're dividing 12 into 3 equal pieces, so it'd be 4th, and 4th power. 4 plus 4 plus 4 gives us 12. So the cubed root of x to the 12th is x to the 4th. Same thing here, dividing it into 3 pieces, x to the 6th, x to the 6th, and x to the 6th. So the cubed root of x to the 18th is x to the 6th. And last one here, 42. I'm not able to think today. 14, there we go. So x to the 14th, x to the 14th, and x to the 14th. So what we're doing with these is dividing the power, or exponent, dividing the power by the root. And I think your textbook calls the root the indice or index. It's just not a word I usually use. The little number in the hook of the radical is your root, and the number on the exponent is the power. So you divide the power by the root, the power by the root, the power by the root. So you just divide. Just like I did here, if I couldn't think of what it was, you just divide the power by the root. So that's all you have to do when it comes to variables. Let's put them together. So the cubed root of 64 we know is 4, and the cubed root of x to the 3rd, so 3 divided by 3, would be just x to the 1st, or you can just put x. You can put the 1 if you want, but typically we don't put it if it's a 1. The cubed root of negative 27 would be negative 3. And 27 divided by 3 would be 9. So again, we're taking the root and then we're dividing. So two separate operations. The cubed root of 343 is 7, and 51 divided by 3, I believe, is 17. Yeah, 17. So the 7 is the root, and the 51 to 17 you divide. Divide the power and take the root of the coefficient. Alright, same idea with fractions. We can separate them into the cubed root of 8 over the cubed root of 125. We know the cubed root of 8 is 2, and the cubed root of 125 is 5. So that's how we get our answer. Here the cubed root of 1 is 1, the cubed root of 27 is 3. Here the cubed root of negative 343 is negative 7, and the cubed root of 512, if we find 512 on our cubes, is 8. So it's actually much quicker with the power chart than with the calculator. So that's just some basics about cubes. We'll talk more about cubes as we go along. And I just want to talk a little bit about fourth roots and fifth roots. We're not going to see these as much, but it's the same pattern. So if we look at fourth roots, we would be looking, again, back at your power chart, your fourth root column. We'd be looking here. So we find 81 in our fourth roots, and we go back to find the base, which would be 3. So the fourth root of 81 is 3, and that's again because 3 times 3 times 3 times 3 is 81. So we're breaking it into 4 pieces this time. For 625, we're going to go to our fourth column. 625, go back, the base is 5. So 5 times 5 times 5 times 5 is 625. So the fourth root is 5. For 1296, we'll go back and look at our base. That would be 6. Trying to type fourth and fifth roots in the calculator is more effort than it's worth. That's why you have your power chart to help you instead. It's so much faster. With negatives, let's see, the fourth root of 16 is 2. If the negative's on the outside, no big deal, just negative 2. If the negative's on the inside, we have a problem, and that's because it's a fourth root. If I were to do negative 2 times negative 2 times negative 2 times negative 2, these two negatives would cancel out, and these two negatives would cancel out, and we'd be left with a positive number. There's no way to get a negative 16 from 4 pieces. So that has a non-real answer. So when you take a square root or a fourth root, we cannot get an answer from a negative, and that's because the even number cancels out all the negative signs. Alright, let's look at the same idea with variables. This time we're splitting it into 4 pieces. I think we see the pattern by now. We're going to do 12 divided into 4 pieces, which would be x to the third. 20 divided into 4 pieces, x to the 5th. And 28 divided into 4 pieces would be 7. Again, you might want to make a note, divide the power by the root. Every time, divide the power by the root. Same idea with fifth roots. Again, hopefully this is getting pretty straightforward. Fifth roots, we look at our 5 column. The fifth root of 32 would be 2. The fifth root of 243 would be 3. The fifth root of 3125 would be 5. So use your power chart. Don't try to type all this in the calculator. It's just not worth your time. Use your power chart with all the numbers already filled in, and you can get these roots no problem. With negatives, we know the fifth root of 1024 is 4. If I put a negative out front, no big deal, negative 4. If a negative's on the inside, let's see if it'll work out. So if we have 1, 2, 3, 4, 5, negative 4, negative 4, negative 4. The way negatives work, these two will cancel. These two will cancel. And it's that odd power, that last one, the oddball, that keeps it negative. So you actually get an answer, negative 4. And then let's look at this with variables. If I'm going too fast, remember you can watch this again. I'm hoping you're seeing the patterning here, and it's just as easy for you as I'm sensing it is. But you can always watch it again, and there's also support online if I'm going a little too quick for you. With variables, again, we're going to divide the power by the root. So 20 divided by 5 would be 4. 30 divided by 5 would be 6. 70 divided by 5, I'm not sure. I should know these things probably. 14. So if you're ever not sure, use your calculator. Don't try to figure it out by hand. I don't know all my multiples of everything, but that can help you just dividing the power by the root. So hopefully you've picked up on some patterns here. So I just want to talk about taking the root of a negative value. So if you have the square root of a negative, or the cubed root of a negative, or the fourth root of a negative, it's when we have a negative on the inside that I want to think about. So we cannot take an even root of a negative value. So square root and fourth root, and it would continue, sixth root, eighth root, all your evens, all of those give you non-real answers. We can take an odd root of a negative. So third root, fifth root, seventh root, you just get negative of the root, whatever the number is. So we cannot take even roots of a negative because we saw those negatives just cancel out. But we can take odd roots of a negative. The odd ones have that last piece that will keep it negative. So you'll see that throughout this homework and practice how that patterning works. So that's just the basics of working with radicals, and we're just going to develop that further throughout the chapter.